Let's move now to multiple regression. The data now are in the form that you have not single x as predictor, but you have k x's and response. So each measurement I, one out of n measurements, would have k different x's and single response y. So the model is linear. The response yi is given as linear combination of all x's. So this is intercept. These are counterparts of slopes. They're not really slopes, but these are coefficients in front of particular predictors. And the error is, again, standard normal with mean 0 and a common variance sigma square. Here, we have k different predictors. We have p different parameters because beta 0 is intercept, is also counted as parameter. So usually in this notation, k plus 1 is equal to p. Classical statistics uses least squares, and this is very elegant. Very compactly, the model is written as matrix X times vector beta plus epsilon is equal to response y. Here y is a vector, y1 up to yn. This matrix X is design matrix. It is n times p. Beta is p times 1 vector. And the error is n times 1 vector. So when you think about dimensions, this is n times 1, this is n times p, this is p times 1, and this is n times 1. So p and p are common, multiplication is possible, and the dimension of this is n plus 1 for all three components. Very elegant least square estimator of beta is given by this expression. This is a least square estimator in which you take transpose of design matrix times design matrix, then you take inverse of this product and multiply by x transpose times y. So estimator is linear function of the observations. Once you get this estimator beta hat, you simply plug into the equation, multiply by design matrix X, and you get prediction y hat. You can also, if you write down matrix H in this form, then you can predict y hat by simply multiplying by H y. And that is called hat matrix because it puts hat on y. The error, residuals, in this case, the errors, empirical errors, are obtained also as linear function of y's. It is identity minus hat matrix multiplied by y. How to find the R square here, and it is quite elegantly. The SST can be represented as this product in which you have y transpose times this householder matrix I minus 1 over nj times y. This matrix is simply identity matrix minus 1 over n times matrix consisting of only ones. SSE is, again, quadratic form involving y and I minus h. Once you have SST and SSE, then you get R square for this regression, or in this case, adjusted R square, which is penalizing for number of different parameters. This is essentially classical approach to multiple regression, involves least square estimation. So what are the Bayesian subtleties? Bayesian multiple regression is straightforward in many respects. You essentially put priors on all parameters, as we know, and the posteriors define the best fit. So the model, as before, is linear. We put the prior on all betas and put the prior on the precision of the error. So how to put these priors? One way to put priors is simply to take independent priors on all betas, beta 0, beta 1, up to beta k, p of those, and simply have these precisions which are really small. And tau, which is the precision parameter of the observation, is taken usually to be gamma with non-informative selection of the A and B. So this is simply traditional way to do it, independent normal priors on betas and gamma prior on precision. If there is weak prior information, there is non-informative prior, we which is essentially putting prior on beta, which is 1 over sigma square. This is Jeffrey's prior, non-informative priors on variance, and flat prior on betas. So that leads to essentially no information about parameters and to posterior inference, which is very similar to the classical inference. Popular method is also so-called normal inverse gamma, in which you have betas which are not independent on the precision or the variance. Conditional on variance, the betas are given multivariate normal distribution. Usually, in this case, this mu is equal to 0 for betas, but not necessarily 0. And there is also covariance matrix that could be given. With this so-called normal inverse gamma because inverse gamma is on variance, but it is gamma on the precision. For this normal inverse gamma setup, the base estimator is simply combination of the ordinary least square estimator that we saw before and the prior mean. Well, actually, if the prior mean is 0, you have the matrix A times the ordinary least square estimator. Matrix A is looking like this, and then you have the influence of the prior covariance matrix. And if the prior covariance matrix is equal to, for example, identity, then this leads to something which is called ridge regression. So very popular way to do linear regression in Bayesian fashion is putting the so-called normal inverse gamma prior. Let's conclude this common priors in linear regression with Zellner's priors, so-called Zellner's G prior. It is normal inverse gamma setup, but then this covariance matrix in the normal inverse gamma setup is taken to be sort of constructed from the design matrix. So this V is going to be x prime, x transpose times x to the minus 1. And then you also put the constants. There is a constant G that actually measures the strength of information. And usually in the so-called, for Zellner's priors, this constant G is taken to be sample size or the number of parameters squared or the maximum between sample size and number of parameters squared.